Okay, this section is a bit longer, 35 slides, and I'll break it into two parts, with the first being an overview of generative AI, and then in the second part, looking specifically at the guts of text, image and sound or music generative AI components. And then we'll look at a sample code in Python of a variational autoencoder, just so you can experience the fun of coding and AI, and then deeper dives in the labs or dev bootcamp after that. So generative modeling is the foundation of generative adversarial networks and variational autoencoders and all of the generative AI that we actually see. Now, I discussed generative adversarial networks in an earlier session, and I'll discuss variational autoencoders coming up, and even show you some sample code, as I said, in Python, so we can see what we're dealing with. Now, both of these architectures are used in image AI, and RNNs, which we covered in an earlier session, are the primary driver of chat AI and sound AI, or sound or music AI. I'll call it sound AI. What I mean by that is music AI extended. But all of these architectures are used, and more importantly, combined in various AI, depending on the goal you're aiming at. Generative AI takes training data, identifies patterns and general dimensional relationships, and then uses the learning and a stimuli, i.e. a prompt, to generate a response of some sort. Autoregressive generative models are dependency models that search for correlation in past data and use that correlation to produce prediction weights, with each new data point causing an update to the next prediction. The heavy lift element inside the foundation of generative modeling is applying statistical and probability distributions to random data to identify correlation, along with many other foundation elements and math, and we'll discuss all of these in more detail in the next sessions. Once again, pay attention to the text on the screen, and I'll add context to the text in my rambling. I may even release a transcript later for you. Okay, the first point says it all. Training data should represent the distribution the neural net should learn. So we want to structure data where the distribution is the model that is exposed by the network, but be forewarned, distributions are only one part of the artificial comprehension needed for generative AI, just like in human learning. We give the AI training data selected to optimize its learning of some specific domain for some specific goal. Then we instigate the AI to deep learn and generate some response to measure its learning. Then we use the variance or error to adjust the learning, i.e. weights, and we try again. We supervise, reward, punish, or use self-aware goals in the resulting variance measurement to improve successive results. At some point, we get an optimal set of weights and then apply them to new data or stimuli to generate a response. So generative AI in a nutshell is learn, ingest stimuli, generate a response to achieve a goal, or basically day-to-day human life. This is how AIs respond to a world of stimuli. As artificial intelligence continues to evolve, the primary goal is to make the comprehension of the stimuli and the response to it more general, i.e. more human-like, and then superhuman or superintelligent. And remember, just because we focus on chat, image, and sound, there is a universe of things we can do with an intelligence system that generates a response to a stimuli. Just look at all the things we humans do. We respond to stimuli all day long. All we need is the response mechanisms like hands and limbs and mouths and eyes and ears, etc. And artificial versions of these are already under development as we speak. Further, these new systems integrate together far better than we humans do today. That's pretty obvious. But we humans still have many advantages as well as disadvantages. One of those advantages is that we can and do evolve. Okay, so let's dive a bit deeper into generative AI. Generative AI is an AI system that responds to variant stimuli in an increasingly general way, or it generates an output. These systems also generally self-learn to some degree. I say generally self-learn, but we know that there are flavors such as supervised or semi-supervised learning, reinforcement learning, etc., etc. And the system continues learning since nothing is truly fixed in life. The true value or gold in a generative AI is the weight matrix, or the output of the learning cycle. That's what costs the money to create, and that's the true value of any generative AI company. The second most valuable thing is the training data, which is currently you and your content and all you do and say and look at online. Sadly, the people in these companies are less valuable and becoming more so in a generative AI investment as the AIs do more code, support, QA, release management, testing, etc. In AI dev, we are actively ending our own careers. But not for a decade or so. So we've got a bit of time. As devs, we too will need to evolve. We discussed GANs in a previous section of this presentation, so these are generative adversarial networks. For variational autoencoders, I discussed encoding earlier, and I discussed a bit about latent spaces in the graphing neural network section, etc., and dimensionality in the sections on abstractions and GANs. It all layers up into this. You can think of a latent space as a set of specific features, like for images, i.e. faces with eyes, ears, mouth, and you can think of words with specific context. In my head, I visualize a latent space as a dimensional space of relationships. Now, I discussed recurrent neural nets in a previous section and autoregressive models in the ChatGPT and other sections. All of this should be familiar to you by this point in these sessions. Now, we are all familiar with some of the uses of generative AI. Image, chat, music AI are the most publicly visible, but there are others. Generative AI systems are also used to augment training data to improve deep learning. They can morph contextual drivers like style. Anomalous recognition, which I talked about in detail in the Artificial Superintelligence Handbook series of books, is assisted by generative AI. Layered systems, where one AI generates input to another AI in a distributed generative structure similar to how humans work, is another application. These are all the foundations of systems that generate new innovation and problem solving, similar to how science uses or should use the scientific method for exploration. It is structured, it is consistent with human cognition, and it is relatively obvious. It's a surprise it took us this long to figure out something so blatantly obvious. So we've discussed different kinds of generative AI, and now we'll dig into what's inside. Not all generative AI use all of these components, but in layered systems you are more likely to find these elements present depending on the architecture. A generator takes a stimuli and generates a response within boundaries defined by the system, such as returns text to a text prompt, or within a context, such as it returns an image to a text prompt. Nothing limits the output from a stimuli except how advanced the system is, and the creativity of the AI architects, because we keep systems contextually consistent. For example, we can use a text prompt to generate contextually consistent video, or a contextual stimuli to produce an emotive response that is contextually consistent. A discriminator in a GAN is another network that tests the validity of the generator's output to the training data and returns a response. It's like a teacher and the generator the student. This is nothing you haven't all seen before in the GAN session. Now, I discussed the latent space before as a lower dimensional or less detailed representation of real-world data. That is, using the features, eyes, ears, nose, mouth, and a value for each to define a face instead of every unique element on every face. When we say sampling from the latent space, what we really mean is using a more generalized input and regenerating an output to match the training data, i.e. setting a metric for eyes, ears, nose, mouth to generate a face. And then evaluating the output variance to the target and backpropagating the error adjustment using the loss function, which you will code in the upcoming labs. Sampling distributions is using the distribution parameters, such as taking an average of training faces and using that to generatively produce various faces around this average or some other metric, and then evaluating the error loss. It has better results with more features like attractive face or popular face, or what is increasing dimensionality or dimensional creep. This is also where we get into AI self-generated human-infused bias, which is rampant throughout all mainstream generative AI systems today. Loss functions include cross entropy for text, mean squared error, binary cross entropy for image AI, KL divergence that we have discussed before for variational autoencoders, and a host of what I would call more novel loss functions and methods, and we won't get into those here. The nature of the architecture of a generative AI is also part of the elements list, such as the various neural networks that I've previously discussed that combine and layer for a generative purpose. So that is determining which components you need to achieve the goal for your AI. Now, obviously, the better the training data, the better the learning, just like it is with us humans. But also, the better the data is abstracted from the real world, the better the generative results. And this is where your talent pool really shines. Get those who really understand or live and breathe this component, and you will succeed far above any team of good coders. Now, I've discussed hyperparameters before, but they include things like batch size and learning rate and a host of newer controls and methods to tune the AI output. Now, we see these in temperature settings for chat AI, and I have discussed tuning AI in more detail in both the Artificial Superintelligence Handbook series and the Tales from Dark Architecture series of books, so more detail out there. Some of the newer methods include things like balance control and degree of acceptable variance and ethical seeds, etc., 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 a bunch of other things that we include. Finally, there's post-processing, which is fairly self-explanatory, as is metric evaluation. You can create any number of metrics with the goal of metrics and measures to provide a degree of relative variance to both help maintain consistency and control the boundaries of the system to improve generalization. An inception score is used in image AI and is a way for the AI to measure quality, or low entropy, and diversity, or high entropy, and create a general measure or metric of such to adjust, with entropy in this case representing degree of variance. Perplexity is a calculation of the variance between anticipated text output probabilities and the actual output sequencing. It's just a method to determine the probability that a string of words makes sense by looking at the probability of any given word with relevance to the previous words. There are an infinite number of ways to formulate a metric, to measure anything. The key is, does the metric measure something valuable to the goal, and how much does it cost in resources and optimization to produce that metric? So let's take a closer look at the generator component in first a GAN for image AI and then a variational autoencoder, also used for image AI and music AI, in a component to component sort of way. Keep in mind that all of these bits and pieces are being continuously tested in various configurations along with new generative methods and architectures to create new generative AI results and systems. So this is ongoing all over the world. In a GAN, the generator is a neural net that instantiates with random data and cycles continuously to improve the output or lower the error. Think of this as a fuzzy picture that slowly improves as features become defined. Transformation we've discussed in more detail in the CNN section. After generating an output, the systems step through an evaluation process to determine the variance between the output and the training data or goal data. We've heard this before. This can be general or direct depending on the hyperparameter settings. This setting diametrically impacts precision and resources and is usually set high in training, that is general image production versus deepfake style training, for example. In a generative adversarial network, the analysis of variance is performed by the discriminator, which is just another neural network. And the result, or variance distance metric, or distance to the goal, is then fed to the generator as reinforcement. The goal of the generator in a GAN is to minimize this distance or variance. In a deepfake, this goal is 0. What we get from the output is two outputs, a generative response on one side and an evaluation metric on the other. And both are very, very valuable for different reasons. For example, detection versus generation. So let's take a quick look at the variational autoencoder. Now, remember, encoding is the act of dimensional reduction or generalization to identify the lowest relative optimized common perception for a given goal. We find a representation that is good enough to get the job done, to avoid wasting resources. It's that whole optimization is overrated thing. In a variational autoencoder, the generator is the decoder to present data points derived from a latent space. A latent space is a lower dimensional feature representation of a learned distribution. So the AI calculates a distribution of data and then identifies consistent patterns based on this analysis or features, and then links the distribution to the features in a form of mapping. When the encoder pushes the input data in this structure through a lower dimensional representation or abstraction, this is known as a bottleneck. What we are really doing is applying statistical analysis to the data so we can then use this analysis to regenerate new consistent data as output using a representation of the data only. So describing an animal by its features until the animal is perceived. It's like that 20 questions game we used to play as kids. So the goal of a VAE is to take samples from the latent space and generate an output similar to the training data, or to mimic, basically. This way, if we ask for a specific image using keywords in a prompt, the AI can interpret those stimuli to generate a detailed image from the lower dimensional, less detailed, and more general prompt. It should be evident that training objective means optimization and generalization. And it should also be noted that the distribution can be adjusted using hyperparameters, different distributions, etc., etc. This architecture is a foundation of in-stream variable flowing stimuli/response, such as video comprehension, motion paths, long cascading context, anticipation/response, inflow style transformation, creative stimuli, and most importantly, self-supervision. So let's take a look at the discriminator in a GAN. Again, this is just another type of neural network that performs a simple real, not real degree classification and outputs a degree metric for this evaluation back to the generator. And by degree, I mean an indication of how far out of real it actually is. The reason for evaluating training data is to provide a grounding point from which to measure reality. Now, this crude self-determined real-world grounding is a step toward AI self-supervision and true AI self-learning, and a very early step on the pathway to artificial self-awareness and self-aware goal setting. Now, this is where you can see our degree of reality with the classification error, and then this degree is back propagated through the network using some specialized optimization methods, of which there are many and we'll cover in the labs. Notice that both the generator and the discriminator improve over successive runs most of the time. They do occasionally go off the rails, and we can see this in the vanishing gradient problem, which I discuss more in the Tales from the Dark Architecture series. I should note that when we discuss latent spaces, the structures captured by the latent space reduced dimensionality are used in areas like image, text, and sound generative architectures, as well as scientific and medical AI, molecular design, data compression, and anywhere you need to differentiate data through a classification mechanism, such as edge detection, interaction, etc. Now, data in the latent space is often stored as a vector of numbers, allowing us to move smoothly between data points in the latent space, or what we call interpolation. And this is also the mechanism to blend different images in image AI, or something I've also written about extensively in Artificial Superintelligence and Tales from Dark Architecture, or state change, especially in flowing context relevance in the newer cognitive AI systems. Now, we discussed a bit about encoding and autoencoders, and that encoding is exposing reduced lower dimensional layers in training data and then using that exposed learning to generate a response to a stimuli. This is the essence of generative AI. I discuss more about autoencoders in the next section of the presentation. But for now, encoding is how neural nets find and comprehend hidden layers in training data, as well as comprehend pathways and relationships between data. This is also the foundation of context in both artificial intelligence systems and humans. If I say the word animal, you will immediately produce in your head a perception of what qualifies as an animal. As I layer more context, like four-legged, this refines your perception in reality. You are using dimensional layers to comprehend a perception. Legs, for example, are a dimensional feature of animals. This is what encoding AI is all about. Now, encoding is the essence of optimized perception, and therefore our reality. And is the foundation of cognition as we explore the relationships between encoded dimensions. In both AI and humans, we use this comprehension to respond to the stimuli we receive from the world, including the stimuli you generate inside your brain as you think about stuff. Everything is related in some way. The key to coding this is to understand how we associate data with context, as we do when we create abstractions and distributions discussed in earlier sessions. Now, I go into the mechanics of encoding in far greater detail in the Dev Bootcamp and in the next section on autoencoding. But know that you do this every single day of your life. Although as you get older, you find new structures less frequently because the depth of your experience, you already know stuff. The idea of encoding is to learn a contextual classification and then use that context to regenerate data based on that understanding. Note that encoding can be simple, as in text generation, or complex, as in layers of cascading context, but this is how a latent space is created in advanced AI. It should be a bit clear to see how in AI we can detect what is in a perception, such as a picture, and the features of each element, and how we can blend or manipulate them to produce something else, something new, something innovative, something creative, etc., etc., etc. So let's review some of the structures of generative AI briefly, as most of this was previously covered in other sessions. Chat AI systems and other text generative systems use basic structures that are changing each day. In general, text-based systems use a model or weights trained on a large language corpus, and these weights update with elements like supervision, bug fixes, and new innovations and new data. These large language models, as we discussed previously, are used to create tokens and the tokens indexed. The embedding layer comprehends the nature of the relationship between tokens with a dense vector. And I discussed all of this in the ChatGPT section and I will do so again in the labs. The RNN structure I also discussed in a prior session comprehends the relationship of words or context in a sequential way. And I've discussed attention and transformers in previous sessions that are used to maintain higher level context over a generative response. So next we move into the generation steps, or initially mathematical wild-ass guesses. This is where the text generator mimics what humans have said before, but with increasing and eventually immense precision. Now the math in a mathematical wild-ass guesses gets better over cycles as long as the training data and algos are good. This is the precision of the AI to mimic humans, and not the precision of the content created by humans that the AI is mimicking. And that is where we see the growth of embedded bias within these systems. In addition to what you see on the screen, there are many new innovations in all forms of generative AI that I go into in more depth in the Dev and Superintelligence bootcamps, so we're just going to cut that off at this point. For now, just know that this reality is wide open and rapidly changing, with many governments and elites trying desperately to reclose Pandora's box. But that is never going to happen for reasons I discuss elsewhere. The final output is a series of responses to the stimuli or prompt that are consistent to the context of the prompt, all in a few seconds. The output is limited in length for now, and contextual cascading, that's multiple layers of context flowing over time, is just starting to emerge and currently carries something called thin context. And if you do not like the output, you can modify some of the parameters like temperature to improve the output. However, there are similar direct parameters available like mood or texture, or indirect parameters within the prompt architecture, such as style, genre, adjectives, etc. And some generative AI have an entire dashboard of adjustments available. And much more just starting to emerge from advanced AI labs like personalized responses. Anyone remember HAL in 2001 Space Odyssey? And you get the idea of personalized AI. Kubrick was a visionary. How about image AI like DALL-E? Once again, we see similar structures that begin with training data and then learning the underlying features and relationships. In image AI, there are different methods to generate images and video that use different methods and tech than text AI, and we cover those architectures in previous sessions so you know how they function. Of course, you can't get to the generator portion without a prompt or a goal, so you need to build a text GPT or some other form of prompt processor, etc., and then use that data to construct the image from the AI's training. This is AI layering, and it's pretty well ubiquitous in advanced AI development and is growing more each day. So this is the same stuff we covered earlier. The image AI implements a CNN as a generator, which we cover in another section of the presentation, to produce images consistent with the stimuli or prompt. What the image AI is doing is taking random noise vectors, which are vectors of random values sampled from a given probability distribution, and using them to produce outputs such as images, like 2D vectors, with dimensions representing image features like color, etc., etc. In text, it is a group of random tokens. In each case, the initial output is improved from the original over successive cycles or epochs. The idea is to use random noise to start the generation and use random noise vectors to alter the output for things like style transfer, denoising, extending data, data augmentation, etc., etc. In a variational autoencoder, once again, they use a distribution representation of a latent space, learned from training, to produce or remap samples from the latent space distribution back into the images. It learns how to go from images to abstraction and then back to images. This way, it can go from a prompt, like a stimuli, to an image or blend of images using the methods I discussed earlier for elements like style and feature manipulation or transfer. This is how you get a teddy bear on a skateboard in New York City in the style of Matisse. That, in a nutshell, is generative AI for images. However, there are many, many moving components, methods, code, training data, and a host of other areas to consider, like optimizing the use of AI-infused GPUs, etc. There is also an entire world that I did not discuss, like motion paths to generate video, or a string of successive, slightly modified images, or for that matter, analyze video, which is matching successive image motion paths to anticipated motion paths. Or another one I mentioned earlier was anomalous events, contextual perception, and generative context. So using context over long periods and multimodally, or over and between various dimensions and sensory perception, so sight, sound, smell, touch, taste, etc. Basically using deep cognition and beyond to eventually generatively producing deep artificial thought. As we move into music AI, or sound generative architecture, you will see the sample structures with modified training data and parameterization. In the case of sound, which includes much more than just music, like voice, gunshot and explosion detection, speech recognition, infrasound, etc., etc., once again, there is an abstraction processing layer, followed by training on the data to determine the feature relationship or dimensions of sound. Sound, like video, is sequential, and it is optimized for recurrent neural nets, discussed earlier, but once again, newer architectures layer different neural nets to achieve more robust AI perception and response. As well, sound in both human and AI systems relies on flowing layers of context or cascades. The layered architecture lends itself to other generative AI goals like human-level contextual comprehension. Like ChatGPT, Music AI predicts the next most likely note of a sound in a generative sequence as determined by its learning on a corpus of existing music and sound. It just predicts the next note in the sequence. It uses as its prompt or seed a bit of music, but more advanced sound AI systems can layer a text prompt that implements a context generator and random sound seed selector, once again layers of artificial intelligence, and then using attention and manipulation alter the generative sound sequencing. Now this permits a sound AI to produce speech from text sample and a name prompt that can then be fed into a deepfake video generation model. Now that's a bit scary and why we all need to own our own voice, image, and data. The same tech can bring long dead people back to life on a full video as long as they have recorded their voice and image somewhere digitally. What makes generative output creative is the randomizers applied to the post-seed processing and the variance of the forward flow with parametric adjustment. Now we've discussed distribution sampling in the prior VAE content, and we'll see a variational autoencoder Python code sample coming up just ahead. Of course, there are lots of elements in a musical score, so as the generative process produces the next sound in the sequence, it is producing a sequence of many elements like tone, pitch, etc., and is manipulating them within a carried context, yet a context that is variant enough to be unique. Temperature is one parameter, but there are many more. This structure can also be used to detect and identify sound. So for instance, score creation output like sheet music, or even to detect deepfakes and dishonesty in human conversation if a flowing contextual comprehension is layered into the structure. Now, I wrote a bit about how AIs detect human lies and deceit in the Artificial Superintelligence Handbook series, if you need more detail on how that stuff works. Having written, played, and produced music in my youth, I can attest that there are lots of subtle variances to creating a score, and even more so in creating a score that is popular. But these are just perceptive sensory variances that an AI can master relatively easily, thereby ending my once budding musical career, luckily for all of you. And the last point, once again, discusses layering of AI systems to achieve a specific desired output. So let's look at a simple variational autoencoder generative code in Python as an overview, and we'll dig deeper into the code components in the breakout labs later on or other boot camps. Now, this VAE begins by importing Python libraries, which we have covered before in other code reviews, so you're familiar with that. Then we set various hyperparameters for the neural net, which we have also shown and discussed in previous sessions and content. Everything you learned in the prior sessions is now starting to layer up. Next, we'll set up a variational autoencoder model. We have two fully connected layers in both the encoder and the decoder, with the encoder putting the data into a mean log variance latent space, and the decoder generating data from that latent space. Now don't worry too much about the detail of the code. You can look it up later, or I'll cover a few of these elements in the lab, or you can just go to the Dev Bootcamp. Focus on the flow of what is happening, the consistency of the action that leads from input to generative output. The so-called reparameterized trick, implemented in the reparameterized method, will sample from the latent space using the mean log variance. The forward method combines the encoder and decoder to take input, encode it into the latent space, sample the latent space, and decode it back. And we create an instance of the model using Atom to optimize it, stochastic gradient descent for all you math geeks, but there are other optimizers as well. We generate some random testing, also known as toy data. We instantiate the training by running batches of data through it for each epoch or cycle. We compute the loss, in this case using mean squared and KL divergence, which we cover more in the labs. And we update the weights as we go, and on completion we print out the generative samples. So basically create data, learn data, apply the learning by creating new samples. The next step is review and adjustment of parameters, seed or training data to improve the overall goal attainment or basically optimization. And this is the output. It's not very exciting, but at least it gives you a glimpse into what is sort of happening inside the machine. Now, once again, there is far, far more to a variational autoencoder than this bit of code. Layers and layers of code and neural networks and infrastructure, but none of it is very complex, especially if you've paid attention in all the sessions. It's just a puzzle of puzzle elements, and once you comprehend the elements and their hidden relationships, it becomes easy. All you need is time and resources, curiosity and drive. Anyone can build these things. To do it at scale requires lots of resources and money, but remember that large-scale empires are usually wiped out by small-scale adventures. You can use these structures to generatively create any output you want, from text, images, and sound to context and even beyond human level cognition. This is the power and the value of generative AI, and it is the foundation of what will soon become superintelligence. Now, I've only scratched the surface of what it takes to build generative AI. There's so much more detail, it would take 10 of these sessions to get through it all just as an intro. There's also so much more that this technology will bring to the world, both good and bad. All of these things you see on the screen are currently in development in AI labs around the world. Now, I can tell you that some of these developments will succeed and most will fail, not due to a lack of desire, but due to a lack of competent talent and money, and the ability to blend the two together to sustain an organization long enough to bring a value to a market. What I can also share is this is going on worldwide by all governments, large tech corps, military, global elites, and small clandestine AI labs. Now, I cover these future items in detail in the Superintelligence Investment Bootcamp, but suffice to say, these exist. They will escape the labs, and AI will self-evolve, whether we like it or not, and completely oblivious to how much phony government control is pushed through. This is a global race to the bottom, a global war for dominance, and nothing is going to stop it. It's both a threat to humanity, and it gives humanity unlimited hope for a much greater, more civilized, free, and sustainable world. We just need to pick the right path forward and the right people to trust. Generative AI is the quintessential double-edged sword.